Welcome to Educator.com. Today is our first lesson for covering radical expressions and equations. And we're going to begin by learning how to simplify radical expressions. First of all, defining a radical expression. A radical expression is an expression that contains a square root. And that expression may contain numbers, or it can contain variables, or both. For example, the square root of 5x, this is a radical expression, and the expression under the radical sign, this right here, the 5x, is called a radicand. A radicand is in its simplest form if it contains no perfect squares other than 1. So if I look at this, 5x, and I try to factor it out, I'm not going to get very far, because the only factors of 5, since it's a prime number, are 1 and 5. So the only perfect square that contains is 1, and that's allowable. And for x, just 1 and x would be the factors, so same thing. Therefore, this is in simplest form, okay? Compare that with the expression, the square root of 8x squared. This is not in simplest form, because if I factor out 8 equals 4 times 2. And since 4 is a perfect square, this expression is not in simplest form. X squared also is a perfect square because it's the product of x times x. So this is also a perfect square. X squared is a perfect square. So this is not in simplest form. Shortly, we'll be discussing how you would change this expression and similar ones into simplest form. Now, a couple definitions and explanations regarding radicals. Recall that there are actually 2 square roots for a number. So if I ask for the square roots of 4, the answer would be 2 and negative 2. And that's because 2 squared equals 4, and negative 2 squared also equals 4. So there are actually 2 square roots for each number, a negative and a positive. However, by convention, when we use the radical sign, we are only referring to the positive square root. So this radical sign means that we're looking only for the principal or positive square root. So when we say we want the principal square root, we mean the positive square root. If I were to be looking for the negative square root of 4, I would express it like this. So then you would take the square root of 4, the positive square root, because that's what the radical is telling you to do. Then you would add the negative to that. And this is the negative square root. So negative square root. So again, when we talk about radical expressions, when you see something like this, it's referring only to the principal square root. Okay, in order to simplify radicals, a very important concept is the product property. And the product property tells us that the square root of a times b is equal to the square root of a times the square root of b. Going back to the example I talked about earlier, the square root of 8x squared. I said that was not in simplest form. So let's take an even simpler radical. Just the square root of 8. I can use this product property to change this into this form and get rid of that perfect square. So first, factor out any perfect squares. So I have 4 times 2. I'm expressing 8 as 4 times 2. Then using the product property, I can split this out into the square root of 4 times the square root of 2. I now have my perfect square separated out from my other factor, and there may be more than one perfect square under here, the products of them, and then the rest of the factors over here. So once I have that done, I can simply take the square root of 4. Again, we're talking about the principal or positive square root, and radical 2. Now, square root of 8 is now in simplest form. Right now, we're going to be writing out each step as you're learning this, but eventually you might just go from this, radical 8, right over to this step. But what's happening in between is actually these steps, using the product property. This same property applies to expressions with variables. So a radical expression with a variable such as 24x cubed. Well, if I look at this, what I have is an expression that's containing a perfect square, because I can rewrite 24 as 6 times 4, and I can rewrite x cubed as x squared times x. So now I have all this factored out, but I need to split off the perfect squares. So I'm going to rewrite this using the product property, and I'm going to rearrange slightly. So before I even write this out, split it up according to the product property, I'm going to cluster my perfect squares. So 4 is a perfect square, and x squared is a perfect square. That leaves me with a 6 and an x. Now I use the product property to get 4x squared times 6x. The square root of 4 is 2, and the square root of x squared is x, and that's as far as I can simplify. So I have 2x radical 6x. So again, the product property is very useful in simplifying radicals. The next topic that we're going to discuss as we simplify radical expressions is what to do when you have the square root of variables with even powers. So we see here that this is 2n, and so when we multiply a number times 2, we end up with an even number. So this tells me that I have an even power. And it says here that the square root of x to the 2n power equals the absolute value of x to the n. Before we address the absolute value, let's just address what's going on here. Okay, so if I want to find the square root of a number in this form that is raised to an even power, the first thing I'm going to do is eliminate the radical sign. Next, I'm going to divide the exponent by 2. So if I had 2n and I divide it by 2, I'm going to end up with n. Okay, so I have this expression radical x to the 2n, so I got rid of the radical sign, and then I divided 2n by 2 to give me x to the n power. The last thing I have to do is take the absolute value of the result. Now, you have to think carefully about why this would be. First, let's just do an example to show how this works, and then talk about why you even need to use absolute value. Well, if you have something such as x radical x to the 10th power, and you want the square root of that, I would eliminate the radical sign, okay, divide the exponent by 2. So here I have 10, 2n equals 10, and what I need to do is divide that by 2. So 2n divided by 2 equals 10 divided by 2, which equals 5. So n equals 5. So now I'm going to get x to the 5th power, and I need to take the absolute value of that result. The reason has to do with the definition of radical. As I mentioned, when we talk about radicals, when you see that radical symbol, it's telling you to take the positive or principal square root of the expression. However, if I don't use the absolute value, I could end up with a negative result. And here's how. If you have a variable, it's representing a number, but you don't know what number it's representing. So let's say that x represents -3. So let x equal -3. Okay, so let's say I have something like this. It's asking me for the square root of x squared. Well, really, what this is, whether I know it or not, is that x is standing in for -3. So let's take this. If I just go ahead and say, okay, I'm going to use the first two steps of this system. I'm going to eliminate the radical sign, and I'm going to divide the exponent by 2. Well, the exponent is 2. I simply divide that by 2 to get 1. Okay, so I got rid of the radical sign. That's going to give me -3, and my exponent is 1. Well, I now ended up with a negative number. That's why you need to add the absolute value. If I take the absolute value, I'm going to end up with a positive square root. So instead of, this is 9, and instead of saying, okay, I end up with a negative square root of that, I'm going to end up with ensure that positive square root by using the absolute value symbol. Now, there's one more aspect to remember of this. Let's say that I go through and I have some expression that I need to find the square root of, and it's to an even power, and I go ahead and find the square root, and it comes out to x to the 4th. Do I need to write the absolute value of that? At the end, it ends up being my expression, whatever was under here, ends up being x to the 4th. And I put my absolute value just as shown above. I actually don't have to do that. And the reason is, whatever x is, if it's raised to an even power here at the end, it's going to end up being positive. If x is -1, for example, let's look at that. X to the 4th is -1. You can end up with 1 times, and then -1, and then 1. Okay, it's going to end up being positive because it's multiplied out an even number of times. So x to the 4th is, even if x is negative, x to the 4th will always be positive. Whereas if I look at something like x to the 3rd, if x, so here x was equal to -1, and if I have x to the 4th, it ended up positive. So I actually don't need to write the absolute value, because in this case the expression x to the 4th is positive. The absolute value is already given. Okay, if I have x to the 3rd, that's an odd power. It's a different story. Because -1 times 1 is 1, times -1 would be -1. So x to the 3rd equals -1. And remember, I don't want to end up with a negative power, with a negative expression when I'm dealing with the radical. Therefore, I do need the absolute value, because the absolute value of x to the 3rd does not always equal just plain old x to the 3rd. If x happened to be positive, then yes, x to the 3rd would equal the absolute value of x to the 3rd. But I don't know that because this is a variable, and I don't necessarily know what the variable represents. Therefore, when you use this system and you come up with your result, which may have multiple expressions, it might be the absolute value of x to the 3rd times the absolute value of y to the 4th times z, the absolute value of z. You really only need the absolute value symbol around the part of the variables that are odd powers. And this will be illustrated in one of the examples. Okay, a second rule that we're going to use to simplify radicals is the quotient rule. The quotient rule tells us that the square root of a divided by b is equal to the square root of a divided by the square root of b. Taking an example to illustrate this, if I have 36 x to the 4th divided by 16y squared, and this whole thing is under a radical, I can use the quotient property to rewrite this as the square root of 36 x to the 4th divided by the square root of 16y squared. Now that I have this, I can see a way to go ahead and simplify. Using the product property, I'm going to look and see what I have, and do I have perfect squares? I do, and I actually don't even need to split them off because 36 is a perfect square. So I'm just going to go ahead and pull that 36 out, the square root of 36 out, and that is 6. And then I have x to the 4th. And remember what we just talked about with even powers. This is going to be x. 4 divided by 2 is 2. And I don't even need the absolute value bar here because this is already even. It's an x to an even power. So this expression x squared will always be positive. 16y squared. I'm going to go ahead and take the square root of that. That's 4. The square root of y squared, just divide 2. And then you end up with the absolute value of y. Okay, so again, you can use the quotient rule to simplify radicals just as we use the product property. Okay, in order for an expression to be in simplest form, in addition to having no perfect squares under the radical, there must be no radicals in the denominator. So the first criteria for having a radical in simplest form is that there are no perfect squares under the radical. The second is that there are no radicals in the denominator. It's okay if there's radicals in the numerator, but not in the denominator. So you need a technique to get rid of a radical in the denominator. So if I have this is not in simplest form. The technique to get the radical 3 out of the denominator is to multiply the numerator and the denominator by the radical in the denominator. Okay, I'm looking at this, and my radical in the denominator is the square root of 3. So I'm going to multiply both the numerator and the denominator by the square root of 3. This is going to give me 7 times the square root of 3, and then square root of 3 squared. Something to remember is that a radical multiplied by itself is equal to the radicand. So if I have, square root of 7 times the square root of 7, which is the square root of 7 squared, this equals the radicand. So two radicals, or a radical multiplied by itself, equals the radicand of that original radical. So here I end up with 7, the square root of 3, and following this property, I know that I actually get 3. Now this is in simplest form because I no longer have a radical in the denominator. I have one in the numerator, that's fine, but I don't have one in the denominator. Okay. Sometimes the radical in the denominator will actually be part of a binomial. So in order to eliminate a binomial that's in the denominator, you need to multiply the binomial by its conjugate. And conjugate means a binomial with the same terms but the opposite sign. For example, just forgetting the radicals for a second, just to be really simple, here's a pair of conjugates, a plus b and a minus b. So just very simple, same terms, but this is the sum, and the conjugate of that is the difference. And the other way around, the conjugate of a minus b is the sum, a plus b. So now looking up here with the radicals, p radical q plus r radical s is p square root of q minus r the square root of s. So same term here, 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 and here, just different signs. Okay, so in order to get that radical out of the denominator, if you're dealing with a binomial, you need to multiply by the conjugate of the binomial. For example, if I have 5 divided by x, radical x, plus 3 radical y, for example, I would eliminate this radical from the denominator by multiplying by the conjugate, by multiplying both the numerator and the denominator by the conjugate. So I know that if I have the square root of x plus 3 square root of y, the conjugate is going to be the square root of x minus 3 square root of y. And I'm going to multiply the top by the same thing. And I'm allowed to do this because I'm just multiplying by 1. And that's the same holds for what we just discussed. The way you can get rid of these expressions, radical expressions in the denominator, is multiplying the top and the bottom by the same thing, so you're essentially multiplying by 1. Okay. Now, we've talked about a few techniques for getting a radical into simplest form, but how do you know when it's finally in simplest form? Well, there are 3 criteria to look at. The first one is that when a radical is in simplest form, no radicals will have perfect squares other than 1. So again, going back to what we used in the beginning, square root of 5x. This does not contain any factors that are perfect squares other than 1. Second on my list, there are no radicals that contain fractions. This meets that criteria. Finally, there are no radicals are in the denominator of a fraction. So this does not have any radicals in the denominator. So whenever you're trying to simplify a radical expression, at the end, double check and make sure that it meets all 3 criteria. Okay, beginning with our first example, and this one does not contain any variables, and this is radical 6 times radical 30. Recall the product property. The product property says that the square root of a times b equals the square root of a times the square root of b. So I'm going to go ahead and use the product property to simplify this. I have the square root of 6 times the square root of 30, and I'm going to change that into 6 times 30. And this equals the square root of 180. Well, this is not in simplest form because a 180 contains factors that are perfect squares. So I'll go ahead and factor this out. And maybe I start out with 9 times 20. I'm not going to stop here because I still have a factor, 20, that contains a perfect square. Because if I keep going with this, I'm going to see that I could end up with 9 times 4 times 5. Now I'm going to use the product property again. I'm going to come back here and continue. And I'm going to rewrite this with my perfect squares under one of the radicals. So splitting this off. And the other factor, which is 5, under the other radical. This allows me to then take the square root of each of these, which is 3 times 2, square root of 9, and the square root of 4, radical 5, which equals 6 radical 5. And just to point out, you could have said, okay, 9 times 4 is 36, and then just express this as 36 and 5, and then you would have ended up with the same thing. But the point is that, you know, if you start out factoring and you don't split it up a certain way, that's okay. As long as you pull your make sure that you pull all your perfect squares out, you can always then multiply them after you have the square roots out here. Okay, so is this in simplest form? I go through my criteria. It has no perfect squares in the radicand. 5 does not have any factors other than 1 that are perfect squares. So no perfect squares other than 1. Okay, my second criteria is that I have no fractions under the radical. So the radicand does not contain fractions. And finally, there are no radicals in the denominator. This expression meets all three criteria, so it is in simplest form. Okay, this time I have a product of two radicals, and this is a little bit more complicated because it contains multiple variables. So start out by recalling the product rule that says the square root of a times b equals the square root of a times the square root of b. So I'm actually going to be going, the square root of a times the square root of b. So for this first step, I'm going to be rewriting this, actually going from this form on the right to the form on the left. So I'm going to rewrite this as the square root of 12 x squared y cubed z times 8 x to the fourth y z squared. Now that I have all this under one radical, I can just go ahead and multiply this all out, and I'm going to multiply 12 times 8 to get 96. X squared times x to the fourth, I'm going to add the exponents to get x to the sixth. Y cubed times y, 3 plus 1 gives me y to the fourth, and z times z squared to get z cubed. Okay, so I'm looking at what I have, and I see that I do have an expression that needs to be simplified further because multiple terms here contain perfect squares. Again, I'm using the product rule, and this time I'm splitting it back up once I figure out what my perfect squares are. Well, once you factor out 96, you will end up eventually with 16 times 6, and 16 is a perfect square. For x to the sixth, we can use and x to the fourth, we can use the rule that we talked about earlier with even powers. So those are perfect squares. So I have x to the sixth, y to the fourth. I'm going to leave those alone for now. Now, z cubed I actually need to express as a factor of z squared and z, because that is not a perfect square. Only the ones with the even powers are. Okay. Next, I'm going to write all my factors that are perfect squares under one radical and the others under another. So that's going to give me 16 times x to the sixth times y to the fourth times z times the square root of 6z. So 6 and z are the two terms that are not perfect squares, so I'm separating those out. Now, let's work with this expression. First, the square root of 16. That's pretty easy. That's 4. Now, recall working with even powers. So if I have a variable raised to an even power, what I need to do is if I have the square root of x to the 2n, I'm going to end up with this, the absolute value of x to the n. So first I have x to the sixth. What I'm going to do is divide 6 by 2. That's going to give me x to the third. I remove the radical sign and I use an absolute value to ensure that I don't end up with a negative, because I do not want the negative square root since there's a radical. And I don't actually know what x stands for, so just to be sure, I need to include that absolute value. Okay. Next, I have y to the fourth. I do the same thing. Remember, the steps are to eliminate the radical sign, divide 2n by 2, and then take the absolute value. This is when dealing with variables with even powers. Okay, so now I have y to the fourth. Eliminate the radical. Divide 4 by 2. That's going to give me y squared. And then use the absolute value. For z, I have z squared. I'm going to eliminate the radical. Divide 2 by 2 to get 1. And then take the absolute value of that. And I can't do anything further with this radical 6z because it's already in simplest form. Okay, there is one more thing I can do to make this even simpler, although it's not required. And recall that I said that you really only need these absolute value symbols for when you end up with a variable that's raised to an odd power. Because no matter what y is, let's say it's -2. -2 times 2 is 4. So I really don't need the absolute value around the variables that ended up being raised to even powers. Okay, this is now in simplest form, and I'm going to go through my criteria. First, I look at my radical that I have remaining, and it doesn't contain any perfect squares. So I can't go any farther with pulling out factors that are perfect squares and then taking the square root of those. So there are no perfect squares within this radical. There are no radicals in the denominator, and there are no radicals that contain fractions. So this expression meets my criteria for being in simplest form. Okay, in example 3, we just have a simple quotient, and recall the quotient rule that says the square root of a over b equals the square root of a over the square root of b. So let's rewrite this as square root of 18 divided by 5. And now I'm going to use the quotient rule to get the square root of 18 divided by the square root of 5. Okay, the problem I have now is that I have a radical in the denominator, and that is not in simplest form. Recall that if you want to eliminate a radical in the denominator, you multiply both the numerator and the denominator by the radical expression in the denominator. So since I have square root of 5 in the denominator, I'm going to multiply both the numerator and the denominator by square root of 5. And this is allowed because if you think about it, square root of 5 divided by the square root of 5 is actually just 1. And you're allowed to multiply by 1. Okay, this is going to give me the square root of 18 times 5. So now I'm using the product property. The product property that tells me that if I have the square root of ab, this is equal to the square root of a times the square root of b. So I went from right to left. These were separate. Now I'm putting them both under the same radical. And in the denominator, I have the square root of 5 squared. Okay, looking at what I have here, let's start simplifying even further. This gives me something that contains a perfect square. So 18 can be re-expressed as 9 times 2, still times 5. And recall that a radical multiplied by itself equals the radicand. So I can just change this to 5. Next step, separate out the perfect square that I had. Now, take the square root of 9, that's 3. One more step, just multiply out 2 and 5. This is now in simplest form. There are no perfect squares as part of the radicand. The denominator no longer contains a radical, and there are no fractions under the radical. So the steps that I had to take were first to use the quotient rule, the quotient property, and rewrite this in this form. Once I did that, then I could eliminate the radical in the denominator by multiplying both the numerator and the denominator by the square root of 5. I then used the product property to rewrite this as the square root of 18 times 5 divided by the square root of 18 squared. Recalling that when you square a radical, when you multiply a radical by itself, then you get the radicand. So this is just 5. Also recognizing that 18 contains a perfect square of 9. So I factored that out. 9 times 2, brought down my 5. Next, splitting off this perfect square under its own radical using the product property, times the factors that are left over, that are not perfect squares, still divided by 5. Take the square root of 9, that's 3, times square root of 2 times 5, divided by 5. One last step to just make this 10, and that is this expression in simplest form. Okay, this time we're asked to simplify an expression that has a radical in the denominator, and that radical is a binomial. Recall that in order to eliminate this, you're going to have to multiply both the numerator and the denominator by the conjugate of this binomial. So the binomial is 3 radical 5 minus 2 radical 5. So the conjugate is 3 radical 5 plus 2 radical 3. So it's the same expression, but this time we are adding instead of subtracting. Rewriting the expression we're given. And all you have to do now is multiply both the numerator and the denominator by this conjugate. 3 radical 5 plus 2 radical 3. 3 radical 5 minus 2 radical 3. So we're multiplying the top and bottom by this expression. Well, I need to go ahead and do some multiplication and some simplification on this. First, looking at the numerator. 2 radical 3 times 3 radical 5. 2 times 3 is 6. Radical 3 times radical 5. Plus 2 times 2 is 4. Square root of 3 times the square root of 3. Now, when I look at what I have here in the bottom, in the denominator, I'm going to recognize that what I have is the difference. I'm going to end up with the difference of 2 squares. A squared minus b squared. So I can go ahead and rewrite that as follows. Minus 2 radical 3 squared I actually made an error. This needs to be a positive. This needs to be a positive. Okay. Because that way, when you multiply out the first 2 terms, you'll get this. The outer term and the inner will cancel out, and then the last will also give you a square, and that's the difference of 2 squares. So this is actually the conjugate you need to multiply by, which has a positive here. Okay, so this is the difference of 2 squares. And now I'm going to go ahead and work with the numerator a little bit more. And I'm going to use the product rule. Recall that with the product rule, I can rewrite this as 6 times the radical 3 times 5. And then here, I'm going to recognize that I actually have 4 times this radical 3 squared, divided by 3 radical 5 squared, minus 2 radical 3 squared. Okay, the next step is 6. 3 times 5 is 15, plus 4. A radical times itself is the radicand, so that gives me 3, divided by 3 squared. 3 times 3 is 9. Radical 5 squared is going to be 5, minus 2 squared is 4. Radical 3 times itself is 3. Continuing to simplify, now we've done the hard part. This is 3 radical 15 plus 12 divided by 45 minus 12 Almost there. 6 radical 15 plus 12 divided by 45 minus 12, which gives you 33. Okay, so this took some work, but staying organized and being very careful to watch your signs when you're working with conjugates, we saw that we had a binomial in the denominator and it contained a radical. So in order to eliminate those radicals from the denominator, we multiply by the conjugate of this binomial. The conjugate is the same expression, but the sum instead of the difference. So I multiplied both the numerator and the denominator by the conjugate. Top expression gave me this. On the bottom, I have the difference of two squares. So I had this. Then I just used the product rule to simplify what turned out to be 6 radical 15. I also recalled that a radical times itself equals the radicand, and that allowed me to simplify all 3 of these because this became 3, this became 5, and this became 3, and then I squared the other numbers, found the products, did some arithmetic, and ended up with 6 radical 15 plus 2 divided by 33. And this is in simplest form. There are no perfect squares under the radical. There are no fractions under the radical. And there's no longer a radical in the denominator. That was our last example for this lesson. And today we covered simplifying radicals. See you soon on educator.com.